Okay, in this activity we're going to continue on dealing with two samples, but in this case we are going to be looking at dependent samples. A case where you have one experimental unit and you're taking two different samples on it. Say we're looking at someone's height versus their fingertip to fingertip distance. That would be one example of paired data, or twins paired data, or a before and after paired data. In this case, we have data lists the ages of actresses when they won Oscars in the category of Best Actress, along with the ages of actors when they won Oscars in the category of Best Actor. The ages are matched according to the year that the awards were presented. So the year is that experimental unit, and we're looking at two different pieces of information: the age of the Best Actress and the age of the Best Actor. Okay, this is a small random selection of available data so that we can better illustrate the procedures of the section. Use the sample data with a 0.05 significance level to test the claim that for the population of ages of Best Actresses and Best Actors, the differences have a mean less than 0. So when we're looking at this data here, we can see that in each of these, looking from one year to the next, the actresses' ages are upper 20s, low 30s. Here we have actors that are, much older. So the speculation is that the difference here is greater than 0, that the actresses' ages in each of these, we could always count on it, the actress's age being less than the actor's age. So that's the speculation. Usually you're not going to be given this information of the difference of the ages. I probably added that. I probably shouldn't have, just because it's misleading. You're not usually going to have that. You could calculate it yourself. I generally like to calculate that myself and then just use single variable data there, but I'm not even going to show you that route. Okay, so when we look at our null hypothesis, this is going to be communicated a little bit differently. So we have that new notation, the average of the differences is how we'd read that. The average of the differences is equal to 0 is our null hypothesis. Our alternative hypothesis is that the average of the differences is less than 0. That's our claim. Okay, our confidence level is 95%. Alpha is 0.05, we knew that. This is left-tailed because we're assuming the actresses are younger than the actors, so we have less than here. We have a sample space of 5, degree of freedom of 4, and our critical value was negative 2.132. Real quickly going to show you where I got that from. We're looking at a one-tailed test, and we want all 5% of our significance, or alpha, in that one tail, and we're going down to 4 here. Our degrees of freedom was 4, 2.132. Okay, so back to our problem. And at this stage, in order to use the formula, you need to have some summary data. And so I want to go into StatCrunch and show you how you can do that with StatCrunch. So if you open up StatCrunch, now if you were doing this on MyMathLab, you could click the little rectangle and it would spill the data directly into StatCrunch, which I already have it in here. So I could go into Stats, I'm going down to T-Statistics, and I want to go to Paired. Okay, my first sample is in the first column, that's where the females are at. The second sample, the actors, are in bar 2. I'm going to go ahead and identify that I want to see the differences. And then I need to go down here and identify that I'm doing less than, and because it's a left tail test, and then I need to click compute, and it did everything for me here. I can see that I've got a mean of negative 10.2. My test statistic is negative 1.55, so forth. And our p-value is higher than 0.05, so we know that that is definitely in a range where we're not going to be rejecting the null hypothesis. If you remember, our critical value was negative 2 point something or other, so this is less than that, or is not in that rejection zone. We'll look at the picture here in just a second. But what I'm pointing out here is it gave me the mean, but not the standard deviation of the differences. And so in order to get that, I can go back up to, now notice I clicked on that button to give me the differences, and so I have a column with the differences. So I can go into Stats, and this time I can go to Summary Stats, and I can do columns, And this time all I want to know is differences for the summary stats for differences. And I'm going to click compute, and that would give me my standard deviation if I would need that. Again, keep in mind that MyMathLab isn't always geared toward what is provided to you with StatCrunch, and so you might have to do a little bit of working around to find some of this stuff. If MyMathLab would ask you for the standard deviation of the differences, I just wanted to show you how you could find that very easily in StatCrunch. I want to go back here, and being I'm in here, I want to go ahead and hit edit, and this time I'm going to go down and do the confidence intervals. And this was a left tail test, and so we had all 5% of our alpha in that left tail. The confidence interval that's going to give me 5% in that left tail and the right tail as well is a 0.9, so I need to click that to get my correct confidence interval, which was negative there. Okay, but what we want to point out is that we've got a lower limit that is negative and an upper limit that is positive, so 0 is in that limit. We can't possibly reject the null hypothesis if 0 is in that. So let's go back to our problem, and I took the formula. Again, you're going to take the average difference, the mean difference, minus the population mean difference that we're hoping is 0, or we're not hoping is 0, but we're testing it whether or not it's 0. So that's where the negative 10.2 came from. This right here. Sorry. I could get it from here, and our standard deviation was right here. So I could plug in my standard deviation down here, the standard deviation of the differences, divide by the square root of the sample size, which gave us our negative 1.55, which we know is much lower. When I go to draw the picture, the critical value on the t-curve, the critical value is way down here in the left tail. Negative 1.5 is on the lower half, but not lower than our critical value, so it's not in the rejection zone. Our p-value, again, maybe I did not make a big deal out of that, is given to us. I have to go back to identify that we want the hypothesis test. Critical value was 0.0973. A lot of going back and forth. I'm sorry about that. And then our confidence interval, we noted earlier that it was negative, lower limit, positive, upper limit. 0 is in that interval. So if 0 is in our interval, and that is what our null hypothesis is, we cannot reject the null hypothesis. So we fail to reject the null hypothesis. There is not enough evidence to support the claim that best actresses are younger. And I hate to say this, I look at this and I go, how can that be? There's only one where the actress was older, 1 year where the best actress was older than the best actor. And I would have to say that that is because this is such a small sample and there is such a wide range among the actors.